And we select Green's function. And the R right? We select that as a Green's function. Then we argue that P at R, which is the position at has to be equal to integration S0 plus S0 minus. That means I am applying that Kirchhoff-Helmholtz integral equation not in this surface, but in this surface. Why this integration is the same as this integration? Why? How can I argue that this integration is equivalent with this integration? As I said in the last lecture. Huh? Symmetric. Right. Okay. If I select this as a Green's function, then the velocity induced by the vibration of this surface and this surface is symmetric. Therefore, the velocity on this imaginary surface is zero, therefore satisfying rigid wall boundary condition. And this integration certainly easier than this integration. Okay? So we have been thinking about equivalent integration surface. Equivalent integration surface. Okay? Then we found that the dGdN on S0 plus and dGdN on S0 minus is equal but having different sign, right? dGdN on S0 as this direction, but dGdN on S0 minus this direction. Therefore, I can say that the magnitude is the same but different sign. And pressure on S0 plus and pressure on S0 minus is the same if the thickness of vibrating cylinder is 0. Right? Or approximately say that the thickness of vibrating cylinder is much smaller than wavelength of interest, and that would be more fancy way to describe what we have. Therefore, this term, note the dr0. If you use that surface of integration, dr0 turns out to be dGdN, right? Okay? And this one is a pressure in normal direction. Therefore, this whole term goes away. So that gives us some idea to use Green's function. Maybe we can always eliminate either this term or this term by wisely selecting the Green's function. Right? If Green's function only requires to satisfy this inhomogeneous equation in addition, then we have such a good freedom to select Green's function. Say I select the Green's function that satisfies this. Then I only have this. And I select the Green's function already, that is 1 over r e to the jkr in this case. Then, if I know the velocity on the surface, that in this case prescribed as un, then this equation just gives me the pressure at any point of r. Isn't it fantastic? Isn't it fantastic? Okay, the result was very striking. The result, PR in the last lecture showed us some magnitude and where R0 is the R0 square is A square plus Z square. What is the physical meaning of this? That means when the sound pressure that I observed on the Z-axis has two components. One is the sound radiating from the center of the vibrating piston. Like there is a monopole at the center. That is e to the jkz component. And another component is a sound radiating from the rim of the vibrating piston. Nothing is really contributing from any between between the center and the rim. Right? That is very interesting. If I away from the vibrating sphere, then this term and this term is approaching. Okay, so in the beginning there is some cancellation. I mean, when this value and this value has a certain value, and the k is 2 pi over lambda, therefore there is some chance to have a zero pressure. Right? So sound, if you draw the sound pressure, it should look like this, and then exponentially decay out as if there is only monopole. So in a far field behavior is very much like radiation from monopole. Right?